So we're going to have a little look at the basics of vectors. So these are just the basic skills that you will use, and you really need to have a good understanding of to be able to answer more complicated questions later on. There's nothing horrible. It usually comes down to a bit of trigonometry and Pythagoras theorem and a little bit of scale drawing. You can have to know both, even if you have a preference for one or the other. Okay, so things that we'll look at then will be how we work out the components of vectors that are at angles, or if we take several vectors and we want to work out what the resultant is, you're basically adding them together and seeing what they do. So we're looking at working out resultants. Okay, just to clarify what a vector is, we have to understand the difference between vectors and scalars. So a scalar is a quantity that you could, things that you measure, that just have a size, so they have a magnitude, in other words, a number. So speed, every type of energy, power, even time, although some people sort of talk about time going forwards or maybe backwards, it's not a physical direction. So they just have a number, they just have a size. That is, in fairness, most quantities. Vectors have size or magnitude and direction. So not only do they have something that tells you how big a force is or how quick a velocity is, but we also can say what direction they're acting in. So displacements, velocities, acceleration, momentum, force, and impulse are probably the main vectors that you're going to need to know. Directions for vectors can come in different forms. So depends on the type of problem you're doing. If it's a two-dimensional one, then you're going to have to give some sort of angle. You could give a compass bearing, or you could just give it as north, south, east, west. Depending on exactly if it is up or down, you can just say things like up, down, left, right. But you can't say it's diagonal. That's not specific enough. You need to give an angle. So that's where the trigonometry comes into it. For one-dimensional problems, so things just along straight lines, accelerating cars and things like that, vectors can be given the direction in terms of positive or negative, and you have to decide what direction you think positive should be. Convention says it's generally towards the right would be positive, and the up, if you're doing up and down, the up would be positive. But if you're dealing with a problem where everything's going down, so dropping things off cliffs, for example, then you might want to make down positive, just so you've not got a load of negatives all over the place. So you can kind of set the problem up however you see fit. Okay, vectors. Vectors are represented by arrows. Remember, they have a size and direction, so obviously the direction of the arrow is important, but the length of it's important as well. If you're solving a problem that involves scale drawings, you need to come up with an actual scale. So, for example, you might decide that 1 Newton is 1 centimetre. So if you've got a force that's 10 newtons, you draw a line that's 10 centimetres long. And this allows you to solve a lot of the problems by scale drawings, but you cannot usually solve them algebraically as well. Very often you have a bit of a choice. You have to know both methods. But to be honest, majority of the time you're going to be solving them algebraically. Okay, so if we add two vectors together, the first thing we're doing is we're taking the line labelled A, which is green, and the line labelled B, which is brown, and we are adding them together to see what they give us. Now notice I'm talking vectors here, not forces. You can do this for any vector. Let's just take this as if it was displacement, so a little bit like distance. You walk the arrow A and you walk the arrow B. Now displacement is just how far you are from where you started. So the first thing you have to do is put the arrows end to end. You can't have two arrows pointing at each other when they are being added. So what I mean by that is that arrow goes to there, and then the next arrow is added on. You can add as many vectors as you want, but they have to go end to end. In fact, it doesn't even matter what order they go in. If you went down B first and then walked along A, you're going to get to the same place. So vectors can be added in any order, but the direction and the size has to stay the same. Now what we're saying here is that this vector R is the resultant vector of adding A and B together. We're not saying that it's a little bit like A and B, it's a bit of an approximation for A and B. In terms of vectors, this vector R is equal to A plus B. Okay? Now, just to clarify what we're talking about. If we were thinking distances, and you walked A and you walked B, you would have walked a lot further than if you'd have walked along R. But distance isn't a vector. Displacement is a vector. And displacement is how far are you from where you started. Well, you started here and you ended here. If you did R, or A plus B, exactly the same result. So they are equal to each other in terms of vectors. So the same is true for velocities. If you'd got a component of velocity that was taking you that way and a component of velocity that was taking you that way, that's exactly the same as if you had one velocity going down there. Forces, probably a bit more obvious. Something pulls you in that direction and something pulls you in that direction. It's exactly the same as if one thing pulled you in that direction with a slightly bigger force. Now, force problems are going to be mostly where you're going to do this kind of thing. The only other one you're going to come across is in projectiles, where you're going to deal with velocities. But that's something to worry about later. The maths behind them is exactly the same. Getting a bit mathematical now, but again, it's something just to be aware of. You can subtract vectors. In a way, it's not really something we do in physics directly, but you do have vectors that are going the opposite way. So that is essentially the same as subtracting. And that's what this is doing here. You've got a vector b, which is down-ish. The vector of minus b would be in the same orientation, but exactly the opposite way. And of course, it has to be the same length. So if you were doing a minus b, you would have a there. And instead of b going down like it did before, now it's going up and slightly back on itself. So now a minus b gives us a different resultant. Incidentally, this being a negative is the way you would deal with it when you're just dealing with vectors that are along straight lines. So you don't necessarily think of it as reversing a vector, but it is exactly the same idea. Okay, one of the most useful tools then is when you can get two vectors that are at right angles, they're perpendicular to each other. Now, quite often you'll get problems where this isn't the case, but we're going to show you something you can do to get all of your vectors perpendicular to each other. So we've got y add x is going to give us r, but because y and x are perpendicular, they form a right angle triangle, which means that r is the hypotenuse of that right angle triangle. So you can just use Pythagoras' theorem, r squared equals x squared plus y squared. The only thing you have to make sure is that you are adding x and y end to end. So you can't have them both coming out from a point and do that. It gets a little bit awkward. Or you can, but you have to think about it in a slightly different way. Okay, so resolving vectors into components. Now, this is just a quick reminder of your basic trig. So your three sort of simple trig rules for sine, cos, and tan. Sine theta being opposite over hypotenuse, cos theta being adjacent over hypotenuse, and tan theta being opposite over adjacent. And the way a lot of us remember that is with SOHCAHTOA. You may have your own way, doesn't matter as long as it works. So if you apply that to this idea of triangles, now, notice what we've done here is we've taken the x and y, and we've made a sort of free body diagram with them. So from this point, y is acting up, and from this point, x is acting to the right. The resultant of those, if you think of these as forces, so that's been pulled up, that's been pulled to the right, the resultant is you're going to be pulled vaguely diagonally in that direction. It will have a very specific angle. So if you were to shift y over to here, you make up a nice right angle triangle. Or you could shift x up to there and you make another right angle triangle. It doesn't matter which you do. R is going to come out in the same direction, the same size. So once you've made your right angle triangle, you know that this is y, and that this is x, and that this is theta. So depending on the information you know, you can use Pythagoras' theorem to get the value of r, and you can use your trig to get the value of theta. Because don't forget, if you're given a resultant force, it needs to have a direction. So, using a little bit of trigonometry, for example, if you had the value of y and the value of r, if you had the value of r and the value of theta, you could use the sine theta rule to get the value of y and figure out what that component would be. So that would be yr sine theta. So just basic trigonometry. Now, there is a bit of a shortcut to this. So to save you having to draw out a triangle and then get the right angle in it and then try and think of which SOHCAHTOA to use and figure out which is the adjacent and which is the hypotenuse. This is exactly the same thing, it's just the result of what we've just said. But it's just something, if you can remember this, if you can memorise it, life will get a lot easier for you, especially when you're doing projectiles. Because in projectiles, you've got to do components, you've got to do speed, distance, time, you've got to do UVAST, SUVAT, and you've got to work in 2 dimensions. If you start that off by trying to remember all the trig rules and apply those, it's an extra level of complication you could probably do without, and this will save you so much time. So this is just my little shortcut. Right, if you've got, I've called it F here for force, but it could be any vector. You've got a force or a vector at an angle. Now, very often, that force is no use to us because it's at an angle, unless you happen to have another force which is at exactly the same angle. You can't add them together. If you've got 2 different forces at 2 different angles, you can't add them. What's easier is if we can break this up into its 2 components. And you need to do this for all sorts of reasons. It's a skill you need to develop. So this is a shortcut. We want the horizontal component. Now in this case, to get from F to the horizontal component here, goes through the angle. So we'd call that F cos theta. So through the angle is cos. Now this just comes from the trig, there's no sort of special trick to it. It's just a case of, instead of having to go through the trig and remember the SOHCAHTOA rules and all that, and apply them, if you can just remember that the component through the angle is cos, so it's F cos theta, if you can just remember that, it saves you time. Conversely, the other side is away from the angle. So that component there, and in this case is up there, is F sine theta. So through the angle is F cos theta, away from the angle, F sine theta. If you can just remember that, genuinely it saves you so much time later on. Okay, so finding the resultant vector. Now actually this is what we've already done. Finding the resultant is just finding out what happens when you add 2 vectors together. So there's 2 ways you can do it. You can draw it to scale. So in that case we have to draw them end to end again. So we've got 1 vector going up there. Now I've deliberately not put numbers on this because it's just showing you the idea. We've got a vector going up there and then another vector going off here. We've got the length of them exactly right to our scale. 100 newtons is 1 centimetre. Make sure you pick a scale that will make the diagram as big as possible but still fit in the space that you've got. You also need to make sure they're off at the right angles. So if it's 33 degrees, you need to measure 33 degrees exactly. If you want to know the resultant, well, the resultant is this here. So you could just measure that distance, use your scale to figure out how big it would be, and you could use a protractor to measure what angle it's at. And you've measured your answer. You can do this for any number of vectors. There could be 10 vectors. As long as you keep your lengths and angles correct, you could measure from beginning to end of any combination. The problem is the more vectors you add in, the more chance there is that it's going to start creeping out of alignment. But again, in exam questions, there's always a little bit of leeway, but you can't beat a really sharp pencil and a little bit of patience for getting this right. We can't add the 2 vectors in this case directly. So let's say if this was like 5 and that was 6, we can't add them and get 11 because they're not in the same direction. Okay, so that's why we have to use an alternative technique. Another way is to have them drawn out from a point. So this is a more algebraic approach. So it makes what we call like a free body diagram. So we have an object here, a force pulling it up there, and a force pulling it down there. And this is where we're going to use the components thing that we've just done. So if we take each of these and we break them into the components, so this force up there at an angle is broken into these 2 components, horizontal and vertical. We can't add the 2 original forces, but I can add things that are in the same direction. So if we do the same thing for the bottom force, a component there and a component down there, I've now got 2 vertical forces and 2 horizontal forces that I can add together. Now you don't have to remove the original forces from your diagram, but you do have to ignore them. So I always like to draw my components dotty so that I can see what's a component and what's an original force, and that way I don't end up missing anything or getting confused. You can get problems like these with 3 or 4 forces on it, and when you split them all into components, it gets a bit complicated. Notice how I've put these 2 components just sort of next to each other. They're not at an angle, it saves drawing them on top of each other, and we can label them separate. So when we add them, think about it, we've got a force up and a force down. So they're going to sort of cancel each other out, so we end up with a very small vertical force. But the horizontal force is both in the same direction, so they added to give us something quite big. So again, think of this in terms of, I keep saying forces, but remember it works with any vector. But if you think of it in terms of forces, we've got a small force up and a big force to the right. So the resultant is going to be something that pulls me roughly in that direction. The resultant isn't there. Now, if you worked out that, you would get the right length. Because if you take this little vector and shift it over to there, it still makes a triangle. So the hypotenuse would be the right size, but it would be in the wrong direction. So you've got to be thinking really carefully about where that resultant is going to be. Now, you could use the proper trig approach if you wanted, turn it into a proper triangle and do that, or you can just leave it as more of a free body diagram and think that this resultant has to combine those two. So it's going to go as high as the vertical, and it's going to go as far along as the horizontal. Now, even though we're doing this algebraically, it is always a good idea to try and sort of draw them to scale. So if you've got a force that's bigger, draw the arrow longer. If you've got an angle that's 25 degrees, make sure it's considerably less than 45. You don't have to measure it, but get them about right. Okay, the other thing is, from here, you can make your triangle up and you can work out the angle. You can actually reverse that shortcut I gave you earlier as well, as another way to do it. That has a tendency to confuse people a little bit, but give it a go. Right, there's two types of problems when it comes to vectors. We have static problems and dynamic problems. Statics is not actually referring to things that are stationary, although it does include that. But it refers to things that are in equilibrium. So for an object to be in equilibrium, it means that it's not accelerating. Now, that doesn't mean it's stationary. It just means it could be moving at a constant speed, and that speed could be 0, but it could be moving. It's just not accelerating. Remember that resultant forces make things accelerate, so if it's not accelerating, there's no resultant force. Another way of saying that is to say that all the forces are balanced. Notice I say balanced, not equal. All the forces are equal might not be true. You might have two forces going up and one big force going down, and they balance, but none of them have the same value. So there's a slight difference in meaning there, just be careful. We tend to forget the other side of equilibrium when we're dealing with these kind of vector problems. So don't forget that equilibrium also is to do with turning forces, so torques and moments. So the second thing that something needs to have, or to be, in order to be in equilibrium, is all the moments need to be balanced, or there's no resultant moment or no resultant turning force. Okay, so for statics problems, the fact that it's in equilibrium, and it might not tell you that in a question, but it might say it's moving at a constant speed or that it's stationary. You know, therefore, that should immediately tell you that the forces are going to be balanced. So if we've got something, object at the centre, and this is the free body diagram, so the forces acting on it are all pointing outwards. If we know that this object is in equilibrium, then these forces balance. Remember, they're not necessarily equal, but they do balance. One way we can check that would be by scale drawing. So if we were to draw these out and put them end to end, they'd make a closed shape. So with the forces, if you followed your way around, you get back to where you started. That tells us they're in equilibrium, that tells us that the resultant is 0. There's no gap. Once you've drawn that shape out, if you actually do it to scale, let's say it wanted to know how big one of the forces need to be to make them balanced, then you could measure your answer. So you could draw out the blue arrow up and the brown arrow down there, and you know that the length of this arrow is the remaining gap. So you can measure your answer, or you can measure an angle. From that shape, it's not right angled, but you could use the sine or cosine rules as well to work out anything that you don't know. So you've got a few options there. The other option, of course, is to do things algebraically. So we could do what we did before. To show that this is an equilibrium, or maybe to create an equation to work out something we don't know, we can use the idea that all of these forces are balanced, but we can't add them together and show that it equals 0. They don't add. They're in different directions. The problem is really these two. They're off at different angles to everything else. What we want to do is turn these into components. So this green arrow here turns into these two dotted components. And this brown arrow here turns into these two dotted components. The blue arrow is actually vertical, so we can kind of leave that one. It doesn't have a horizontal component, so we'll just leave that one as it is. But now we've got just horizontal and vertical arrows, we can add them together. So we can simplify that down into something that's just got two components, and we can find the resultant of those two components, and we can find the angle like we've already done. So this whole components thing is a very useful tool in a lot of different ways. Right, dynamics problems, you use a lot of the same skills, but the difference is there's now a resultant force. Now, having a resultant force very often, but not always, means you might be using the equation F equals ma. It certainly does mean the object will be accelerating. But you could just be finding what the resultant force is. But sometimes if you've got an acceleration, it means if you know the mass of it, you can work out what the resultant force is and add that into your force diagram. You just have to be aware that now the forces are not balanced. So therefore you can't say that they are, you can't make an equation where you equate things together. You have to kind of put them into an F equals ma, or find the difference between two forces and put them equal to the resultant force. So it's just a slightly different approach, but it does require a little bit more thought. Okay, general approach to problems then. Firstly, draw really clear diagrams. Make sure you don't miss any forces, especially things like normal reaction forces sometimes can be very easily missed in certain problems. If you're only looking at a car problem and it's only really interested in the friction and the forwards forces, then nobody cares about the weight and the normal reaction forces. You can just concentrate on the bits you need to. But for things on slopes, try and think of all of the forces. Get them all in your diagram, nice and big, clearly labelled, any values that you know, any angles that you know. Get the lengths of the arrows to be about right. Get the angles to be about right. And it all makes it a lot easier. Once you've got a free body diagram, if it helps, you can sort of redraw it or maybe simplify it down. A lot of people sort of copy the diagram that they're given with all the extra details of children sitting on seesaws or whatever. Simplify it down to simple lines or dots, have all the arrows coming out from the middle. Or draw them end to end if you're doing a scale drawing. Like I said, make the sketches roughly right. It's so much easier to see if you're getting something wrong if you can kind of see what the answer is just from your sketch. If you've got any forces that are at angles, this is if you're working algebraically, just immediately break them down into components. When I'm doing these sorts of questions, if I've got a force at an angle, the first thing I do is work out what the two components, horizontally and vertically, or whatever's appropriate, would be, before I've even really read the question. I probably should read the question, but it's just automatic. I just work out the two components, and then all the information I need's there when I come to answer the question. Just check for any other information. So any reference to this being at constant velocity or uniform motion, or it's accelerating. Those things will tell you whether you're dealing with a statics problem, in which case all your forces are balanced, or whether you're dealing with a dynamics problem and you need to build slightly different equations. Acceleration means there'll be a resultant force. If it's constant speed, remember, that's still an equilibrium. It's still a statics problem. Once you've got your diagram sorted, you can then build equations. So that's if you're doing a problem algebraically. You can, for example, work horizontally and build an equation which puts all those forces up equal to all the forces down, and then you can do another one vertically. And with all that, you can then solve to find whatever it is that you can't find. Sometimes that gives you a problem where you've got simultaneous equations, but you just deal with the simultaneous equations. Okay, just the last slide with a reminder of the equations for this one. So the sine and cosine rules for non-right angle triangles. And then just the SOHCAHTOA and the Pythagoras theorem for the rest. So, whilst it's a bit complicated, these are real important fundamental skills that you will need in a lot of questions in mechanics. So make sure that you're really, really happy with the examples that we go through in the lecture. Okay.